Thank you for introduction. I start the presentation. In our work, we try to deal with while statement in Rocq. The challenge is that the limitation, that is, Rocq doesn't permit the definition of non-terminating function. For example, let's consider collapse predicate, whose halting problem is an open problem. Since this function is non-structural recursive function, we can't take a fixed point by using fixed point command. And due to lack of termination proof, we can't use equation command. And it is true that we can define this function by using fixed point command, but it is co-inductively proving the properties for this co-inductively defined function involve complex proofs with co-induction. So we propose a more simpler way to deal with this function containing while loops, while statement. Our idea is executing while by monadic rewriting. Firstly, I explain the background. Monad is a weather method for expressing computational effects in functional programming. FMA consists of functor n and operators let and bind. The functor express the results of computational effects, and let gives a trivial effect to a value, and bind combines two effects through computation. And the operator let and bind are characterized by the monad law, three monads law, bind let F, bind M let, and bind A. Monadic equational reasoning is an equational reasoning for effects through computation with such monad law. And its formalization, Monad is a monadic equational reasoning library in Rocq. Monad A consists of interfaces and models. The interfaces is used for equational reasoning, and models is used to guarantee the soundness of verification. And Monad already supports probability mod and non-determinist monad and so on. For example, the interface defines the state mod like this. The interface defines the operator get put and defines the equation for these operators, put and put get and so on. And models defines the concrete model for this operator, get put, and gives a proof for equations. By separating interfaces and models, the implementations are hidden to user, so we can write simple proof based on rewrite tactic. In our work, by considering non-terminating behavior as an effect, we extend Monad library to express while loop. The advantage of verification is as follows. We can write proofs using a rewrite tactic, and we can combine some other effects using Monad transformer. For illustration, I explain using the factorial with while loop and reference operators. In Monad, the factorial is expressed like this. The while related part is expressed by while operator, and reference related part is expressed by CNU, CGET, and CPUT operator. We can both use while operator and reference related operator at the same time because of combination using Monad transformer. Firstly, I explain the interface for the while operators. We define the interface based on complete ergot model, which treats recursive structure algebraically. The complete ergot mod has operator while, which corresponds to while loop. And the while satisfies 4 actions, fixed point E, naturality E, diagonal E, and uniform E. Each action represents the while loop behavior. For example, fixed point E means represent the loop unrolling behavior. This row is the equations like this, and the equation means if the body X is evaluated to left embedded value, then the while loop terminates with the value, and if the body is evaluated to right embedded value, then the loop passes, the value is passed to next while loop. Now we explain the usefulness of this interface using the example Makasi91 function. Makasi91 function is defined recursively like this. Yeah. If n is more than 100, then n is decreased by 10, and otherwise it recurs doubly with n plus 11. But it has good property that is for any input n less than or equal to 101, this function always returns 91. For example, for 98, it is calculated like this. In the calculation, Makasi91 function repeats increasing and decreasing the argument. So in Rocq, we can't define this function directly, but by using the equation based on complete ergot mod, we can prove the always returning 91 property in Monadic. Firstly, we explain Makasi91 function by loop. This function is represented by y like this. It with argument n and m. N is the depth of recursion and m is value. If m is more than 100, n is decreased by 1 and m is decreased by 10, and the otherwise n is increased by 1 and m is increased by 11. So the body function is defined like this. If n equal 0, then it returns left embedded value, and the otherwise it returns increased right embedded value or decreased in right embedded value depending on n. Essential property for always returning 91 is the property that is if m is more than 89 and less than 101, Makasi91 m is equal to Makasi91 m plus 1. This is proof like as follows. Makasi91 m is equal to this by definition of this function. Then we can unroll the while by using fixed point row like this. And the if state by using the assumption on n, we can calculate the if statement path because m is less than 101. Then the both red and bind appears. So this term is translated by using bind red flow. The form of this term is similar to the first term. So by repeating this process, we can obtain the result we want. After this point, I explain the verification using complete ergot-mode interface. So from now, I explain the soundness of verification, that is the model. The model, in our work, we use delay mode as a model. The delay mode consists of function delay, which maps types A to maximum fixed point of x equal a plus x. In Rocq, we can define this function by using co-inductive command with constructor dnow and dlater. Intuitively, dlater expresses one step of computation. But to know about the computation results, the explicit computation step dlater is unnecessary. So we introduce relation W by C to judge the computation equivalence. That is, if D1 and D2 are related by W by C, if D1 and D2 are equal, ignoring finitely many applications of dlater, or both D1 and D2 are the results of infinitely many applications of dlater. The first case means D1 and D2 terminates to the same value, and the second case means both D1 and D2 diverge. And the monad operators of delay mode is defined like this. The return is the dnow constructor, and bind is defined by using cofix point command. Bind returns fa if only if m equals dnow a, and otherwise it removes one dlater in n. Next, I explain the definition of while for delay mode. While is also defined by cofix point command and defined like this. If body A is evaluated to right embedded value, it returns one dlater applied while loop, and if it is evaluated to left embedded value, it terminates with the value. And this operator satisfies four completed ergot-monad laws. For example, we can easily check this definition satisfies fixed point E law in case that body X equals let in Ry. While body X is equal to this, and since body X is let in Ry, it is calculated to dlater while body Y. And the difference between dlater while body Y and while body Y is one dlater application. So dlater while body Y is related to while body Y. And this is equal to right-hand side. So we can see the while operator satisfies fixed point E law. The express up to this point, we explained the Y-related part in first factorial example, but the reference-related part remains. So we combine completed while part with reference-related parts using monad transformer. A monad transformer converts one monad into a new one, and monad already supports a monad transformer. In our work, to represent reference-related part, we use type monad transformer. The type monad transformer is introduced for expressing Occam's reference, and this monad has operator CNU and CGET and CPUT operators. And the monad transformer, and this monad transformer is defined as a composition of state monad transformer MS and exception monad transformer MX. And the state set point is the record of value and type, and set point models type store. In our work, state monad transformer and exception monad transformer, we showed MS and MX preserve the complete ergot monad structure, so it leaves the MTX preserve complete ergot monad structure. This is conclusion slide. Thank you for listening.